Okay, it is 3 o'clock and we can start. So welcome everyone and thank you for attending the Control Seminar Series. Today we have a very wonderful speaker, but I will start before with letting you all know that if you are enrolled into MAE 205, please log in using your full name. That way we will be tracking attendance. And if you need the recording of this seminar, please contact me via email and I will send it to you. Thank you very much. Professor Herbert, the floor is yours.
Okay, great. I'm delighted to introduce our speaker today, Professor Aniruddha Majumdar. Ani did his PhD with Russ Tedrick at MIT. That's right, yes. And then after that went and joined with Marco Pavone at Stanford for his postdoc. And then now is a professor at Princeton, going on, I think, 5 years now. Ani's always been really interested in trying to really push the performance of robotic systems while maintaining safety guarantees. So a lot of us, when we work on safety, we end up with these very, very cautious, nervous robots. And Ani does not do that. So he is kind of blew us all away with his safety funnels techniques, where he has very agile robots being able to navigate quickly while maintaining safety, and has since explored all sorts of different areas. And has become an expert, not just in his background of doing sum of squares optimization, but has really now incorporated in how through the stack of perception to estimation to control, how we can push the limits of the hardware on robotic platforms while maintaining some rigor in what we can say about the results of them. And so I am, and I guess one side note is, on a personal note, everyone has always been really impressed with Ani as a researcher in terms of being one of the simultaneously most productive people while also being one of the most calm people possible. And the ability to be able to do both at once, I think was an inspiration for us all. So with that, I'd like to introduce Ani.
Thank you so much, Sylvia, for the really nice introduction. Let me share my screen here. Yeah, thanks for the introduction and for the invitation to present our work at UCSD. So I'll be presenting some of the work we've been doing, as Sylvia mentioned, on enabling agile robotic systems, things like unmanned aerial vehicles, to operate with guaranteed safety and performance in complex environments. And over the last few years, we've been thinking about how do we make guarantees on safety and on performance for robotic systems, which have learning-based components as part of their perception or control loops. And that's the work I'm going to be presenting here today. So the last decade or so, there's been a huge amount of excitement in machine learning and the intersection of learning and robotics in many different domains and applications. So for example, robotic manipulation, UAV, obstacle avoidance and navigation, and also, of course, autonomous vehicles. And I would argue that a lot of this excitement in learning and deep learning specifically has been due to the ability and the power of these techniques to handle rich sensory inputs. So to process things like visual inputs or depth images and turn them into representations, which can then be used for downstream tasks such as planning or control. And the work in this area, the progress in this area has been extremely exciting. But I think if we look at some of the state-of-the-art robotic systems that have learning-based components in their perception or control loop, we find that there's still a long way to go. So I imagine many of you have seen OpenAI's robotic system for solving a Rubik's Cube with one hand. So extremely impressive demonstrations of fine kind of manipulation. But if you look at the success rates that this system achieves, it ranges from about 20% to 60%, depending on the complexity of the task. So basically, depending on how you initialize the Rubik's Cube, how many moves the system needs to make, the success ranges from about 20 to 60%. Here's another example in a kind of autonomous driving scenario. So this is one of Tesla's cars that's driving down a road at evening time. And the interesting thing here is if you look at what the perception system of the car is reporting, it's basically looking at the moon, which is kind of slightly low in the sky, and saying that this is a yellow traffic light. And that's actually causing the car to brake. In this case, if you look at the kind of bottom portion of the video, the human driver is overriding this braking command and keeping the car going. But it's still a pretty kind of scary error that this perception system is making. Here's another example, again, in the domain of autonomous driving. So this is one of Tesla's cars driving on a pretty standard road on a bright and sunny day. And this full self-driving system makes the car veer wildly to the left. Again, in this case, the driver was alert and took over. But again, a pretty scary potential outcome that might have happened. So I think if we analyze some of these videos, some of these failure cases of learning, what I would argue is that these are really examples of failures of generalization. So these systems were trained either using reinforcement learning, so countless hours of simulation experience for the OpenAI Rubik's Cube system, or supervised learning for a perception system for an autonomous vehicle. These learning systems were trained on some finite amount of data. We're then taking these systems and deploying it in new settings, new environments, and they're basically failing to generalize. And I would argue that current learning-based robotic systems have trouble generalizing even to mildly different environments than the ones that they were exposed to during training. And I think this is a really fundamental technical challenge, this challenge of generalization to new environments. I feel is fundamental if we're trying to think about safety in the context of learning and robotics. And I feel like we need to provide some guarantees on generalization, some formal guarantees if we're deploying these systems out in the real world. Okay, so just to pose the problem of generalization a little bit more carefully, I'm going to present a concrete example that I'll use as a running example throughout the talk. So imagine that you have a UAV and you're training it to navigate through some cluttered environments. And maybe you're training a neural network policy that takes in as input a depth image or some visual input and takes control actions based on that. And imagine that you're training this neural network given some data set. So maybe in this case, 1,000 different environments that you have the geometries kind of mapped out for. The question that we're interested in is what happens if you train the system on the 1,000 environments and then you deploy it on the 1,001st environment. So in a new environment that was not part of the training data set of your learning system. So can we guarantee that the robot will succeed with high probability maybe in this new environment? So in this talk today, what I'm going to present are some of the approaches that we've been developing in my group for making such generalization guarantees. And we're particularly interested in settings where your robot might have nonlinear or hybrid dynamics, and specifically also rich sensory input. So I think this is primarily where the power of learning comes from to handle things like vision or depth. And so we want to handle systems that have RGBD images, for instance, as observations, and also neural network-based control policies. And my goal today is basically to convince you that it's possible to make some non-trivial and meaningful guarantees, even in these kind of general settings. So there's been a lot of excitement on this topic of safety and learning in robotics. And a lot of this work has been kind of under the umbrella of what's known as safe learning. So the problem of safe learning is essentially to ensure that your robot doesn't violate any safety constraints while it is learning. So as a concrete example, if we think about a UAV who's learning to maybe perform a certain maneuver in a given environment, the goal here would be to ensure that as the robot's policy gets updated, so as it is learning, it doesn't violate any safety constraints. So it doesn't collide with the obstacles of the ground, for example, as it's updating its policy. And there's been a lot of really exciting work on this topic from Sylvia and others. So for example, based on Hamilton-Jacobi reachability theory, robust MPC, Gaussian process regression, and also formal methods for tackling this problem of safe learning. But the problem that I'm going to focus on today is a little bit different from this problem of safe learning. So the kind of basic formulation of safe learning considers safety or ensuring safety during the training process. So as the robot is learning, updating its policy, can you maintain safety? The problem that I'll be more focused on today is can we ensure safety not during training, but during testing or deployment in new environments that were not part of the training data set. for your robot. So this problem of generalization. And I think these two directions are complementary in many ways. You could potentially combine the work on safe learning, which ensures safety during training, with some of the work that I'll present today on safe generalization to new environments. So here's the formal problem statement. So I've kind of sketched this problem of generalization. I just want to define it a little bit more formally. So imagine that we have some robotic system with some dynamics. So X here is the state of the robot, U is the control input, and E is an environment that the robot is operating in. And these dynamics could potentially be nonlinear, could potentially be hybrid. And I'm using the word environment here pretty broadly to refer to factors that are external to the robot. So if you're thinking about UAV navigation, think about the building that the robot is navigating through as corresponding to the environment. If you're thinking about manipulation, think about the object that the robot is manipulating as corresponding to the environment. So the main assumption that I'm going to make, at least for part of the talk, is that there's some true but unknown distribution D from which your environments are being generated. So this distribution could be extremely complicated. We don't have direct access to it. But I'll assume that we have some access to a data set of finite environments that are drawn IID from this true but unknown distribution of environments. Your robot then has some sensor. So again, we should think about rich sensing modalities, for example, vision or depth. So your sensor observation Y depends on the state that the robot is in and also the environment that it's operating in. And our goal then is to find a policy, to learn a policy that maps sensor observations to control inputs in order to minimize a certain cost. So this notation C pi E here is the cost of policy pi, so running a policy on a given environment. And I'm going to assume that the costs here are bounded. And without any further loss of generality, I'll just assume that they're bounded between 0 and 1. So in this kind of running example of UAV navigation, you can think of assigning a cost of 0 if the robot successfully avoids obstacles and gets to a goal, and a cost of 1 if the robot collides with an obstacle. Another assumption that I'll make is that for any policy pi, we can evaluate the cost that the policy incurs just on the training environment. So we can basically run any policies on the finite set of training environments that we have and evaluate the cost that a policy incurs just on the training environments. So okay, with that setup, the goal then is to learn a policy pi, which minimizes the expected cost across novel environments that are drawn from this underlying unknown distribution over environments. So we want to minimize this expectation taken with respect to this unknown distribution. In certain cases, it's going to be slightly more mathematically convenient to find not just a single policy, but instead to try to optimize a distribution over policies to minimize the expected cost across novel environments. So in this formulation, there are two expectations. The inner expectation is because we're randomly selecting some policy from a distribution that we will optimize. The outer expectation is the main challenge here. So this expectation is taken again with respect to this unknown distribution D, from which environments that your robot will encounter are generated. So the main kind of technical tool that we've been exploring in my group is what's known as generalization theory. So this comes primarily from theoretical machine learning and primarily has been developed in the context of supervised learning. So things like image recognition tasks. And the main kind of technical idea will be to translate and extend some of these results from supervised learning to the control kind of formulation that I just presented a couple of slides ago via reduction-based approach. And basically what this theory will allow us to do is upper bound the quantity that we're interested in. So we're going to upper bound the expected cost across novel environments drawn from this unknown but underlying distribution over environments. And our algorithmic approach basically then will be to find some policy or distribution over policies that will minimize this upper bound to basically give us the best possible guarantee on generalization performance. And we can do this in certain cases via convex optimization, and in other cases via stochastic gradient descent or black box optimization, so derivative-free optimization. The specific generalization framework that I'm going to be describing here today is what's known as PAC-based theory. So PAC stands for probably, approximately correct. And again, most of this theory has been developed in the context of supervised learning, things like image recognition tasks. And it turns out that PAC-based in particular provides some of the tightest known generalization bounds for classical supervised learning approaches, things like support vector machines. And more recently, over the last 3 or so years, there's been a resurgence of interest in PAC-based for explaining and also promoting generalization for deep neural networks, again, primarily in the context of supervised learning. Okay, so I'm going to describe PAC-based theory. So I want to make sure if you haven't seen PAC-based theory before, you leave this talk at least having understood the main result from PAC-based. I'll first present it in the context of supervised learning, and then I'll describe how we can extend that to the control kind of formulation that I presented. So in the supervised learning setting, we have some input space and some label space. So you can think of the input space as the set of all images, for example, and the label space maybe as corresponding to object categories in an image recognition task. Again, we'll assume that there's some true but unknown distribution D over your inputs. And this could be extremely complicated, the distribution over all images that you might encounter. So we don't have kind of direct knowledge of this distribution. And our goal is to find a hypothesis which we could parameterize, for example, using neural networks. So weights of neural networks might give you a kind of parameterization of the class of hypotheses that we're working with. And we have some loss function that basically tells us how well any hypothesis does on any given example. So PAC-based theory then applies to learning algorithms that have this following general structure. Instead of finding a single hypothesis, what PAC-based tries to do is find a distribution over hypotheses. So the first thing we're going to do is specify a prior distribution P0 over hypotheses before observing any data. So if you're thinking about neural networks, imagine that you have some network architecture parameterized by weights, and we choose some prior distribution over the weights of your network. We then observe a data set, so some finite data set of inputs and labels. And based on the prior and the data samples, we choose some posterior distribution over the weights of your neural network, some posterior distribution over your hypothesis space, and I'll call that capital P. And I guess one point I'll mention here is that even though I'm using the word prior and posterior, the posterior is not necessarily a Bayesian posterior. So the result that I'll present is going to be valid for any posterior distribution, not just the Bayesian kind of update. And the guarantees we're going to end up with that PAC-based will help us make are kind of a frequentist in nature. So yeah, I'll say more about that on this slide. So let's define our training loss. So this is the loss incurred by our posterior distribution just on the training examples, which we have access to and which we can then evaluate. The quantity that we're really interested in is the true expected loss. So again, this is the loss on future expected loss on future inputs that are drawn from this underlying distribution over inputs. This is the main kind of result from PAC-based. So it tells us that with probability 1 minus delta, where delta is a parameter that you get to choose over the sampling of the training data set, the following bound holds. So we can upper bound the quantity of interest, the true expected loss on future data, as a combination of the training loss, which we can evaluate based on our training data set, and an additional term, which sort of looks like a regularization term. And the main quantity in this regularizer term is the KL divergence between the posterior and the prior. And basically one way to think about this is that this is preventing overfitting. So it's saying don't make your posterior too far away from your prior in order to fit the finite amount of data that you happen to have access to. So that's the kind of basic result from PAC-based. What I'll describe next is how we can take this result and translate it into the control kind of setting that I described a few slides ago. So again, in the supervised learning setting, we have some input, maybe corresponding to an image. We have a hypothesis that takes the image, maps it to a label. We have a loss function. And
sorry, Annie, could I
sorry,
ask you, could you just go back one slide, please? I just
Absolutely.
want to try to understand. Given that nothing is assumed about the D distribution,
Yes.
I presume the delta is in the P distribution. It's a distribution you know about, right?
So D is unknown. The only kind of knowledge we have about it is indirectly through the finite training data set, which is drawn kind of IID from this underlying distribution.
So there's an assumption that the training data set's representative then?
Yes, absolutely. Yes, definitely.
Okay, thanks.
Yes. Good. Good. Yeah, maybe I can pause actually and see if there are other questions on.
Yeah, I have a question.
Yes.
So regarding the loss function, so are there any assumptions on the loss function?
Yeah, good. So the only assumption is boundedness. So there's no Lipschitzness, for example, which some other frameworks often assume. This is, I think, one of the benefits of pack-based. So the restrictions are relatively loose.
And then just to confirm, no assumptions on the unknown distribution regarding tails or anything like that.
Yes, exactly. Yeah, exactly. Right.
Okay, great.
Except the training data is representative.
Yes, and that is a big assumption, and I'll say more about that.
So you can't have a training set which is not drawn from the D density in a representative fashion. You really can't say anything.
Yes, good. Yeah. And I'll say a little bit more about potential ways of addressing that in a little bit.
So question, maybe I miss it, but how do you formalize representative, right? Being representative. I understand the intuition, but how?
Yeah, so representative here just means IID. So the training data set, each sample and the training data set is drawn IID from this underlying.
I see. That's okay.
Good. All right, other questions on this? Okay, so yeah, I guess what I was describing is how to map the setting that we're really interested in, which is the policy learning setting, onto the supervised learning setting. And the way we will do this is by thinking about the environment that your robot operates in as corresponding to the input in the supervised learning setting. We then have a control policy which indirectly maps environments to actions indirectly through sensor observations. We have a cost function that tells us how well any policy did on any given environment. And basically with this mapping, which I'm presenting just informally here, we're able to derive a guarantee, so an upper bound on the expected cost of a policy or distribution over policies on new environments. And this is kind of the analogous result in the policy learning setting. So similar to the supervised learning setting, we can define our training cost as the expected cost on the training data set that we have access to. The main quantity of interest, again, is the true expected cost on future environments. And again, we can bound the true expected cost with probability 1 minus delta as a combination of the cost incurred on the training environments plus this regularization term. And basically the main kind of algorithmic idea here is then to find some posterior distribution over policies that will minimize this upper bound on the true expected cost. So the true expected cost is not something we can compute directly, but we can, under the assumptions that I've laid out, compute this upper bound. So we want to find some posterior distribution that will minimize this upper bound to give us the best possible guarantee on generalization performance that we can get. For certain settings, so if you're optimizing a distribution over a finite number of policies, we can minimize this upper bound from pack-based using convex optimization, so particularly geometric programming. In a more kind of general setting, if you're training neural networks, what we do is basically parameterize posterior distributions and prior distributions by specifying distributions over the weights of your network. So think about Gaussians, for example, on the weights of a neural network. We can then minimize or try to minimize this upper bound on the expected cost using stochastic gradient descent or other approaches, for example, based on black box optimization. Nikolai, question?
Yeah, I wanted to ask a quick question. So in this analogy between the supervised and the control setting.
Yes.
Here it's difficult to sample environments. I presume in practice we can only get observations of them instead of direct environment samples, and there's some error or uncertainty in the observations as well, which I guess it's not captured right now. So is that a problem, and is that something you've thought about as well?
Yeah, that's a great question. So I think in the context we've been mostly thinking about, which have to do with navigation or manipulation, I think in these settings it's reasonable to say that we have kind of good knowledge of the training environments. So it might be a lot of effort to collect this information, but there are some existing data sets. So I guess one of the pictures I showed before were from the Stanford like 2D, 3D indoor data set, where they basically took a Matterport camera and like scanned pretty carefully the insides of a number of buildings.
Yeah. Okay, I got it. So we assume for now we can get environment samples directly.
Yes, but I think that's a great question. If you cannot do that, then some of this might break.
Thanks.
Good. Other questions on this so far? Okay. All right. So let me present some results, I guess, to demonstrate the kinds of guarantees we're able to get with this theory. So the first example is going to be in the context of quadrotor navigation. And the goal is basically to be able to demonstrate that we're able to get some reasonably strong guarantees on generalization performance when you have neural network policies that you're optimizing or learning. And also when you have kind of rich sensory inputs, so RGBD images in this case. So this is purely in simulation. We're simulating both the sensing, the RGBD images, and also the nonlinear dynamics of the quadrotor using the PyBullet simulator. And in this example, we're implementing a receding horizon control architecture using motion primitives. So we have some number of motion primitives that we've pre-computed for the drone. So you can see this in the bottom right picture. So these are basically things like fly straight, turn left, turn right, and so on. And at every point in time, we have a neural network which we're trying to learn, which takes in the RGBD image or a sequence of RGBD images and basically maps that to a selection of the motion primitive, which then gets executed for a little bit, and then you replan again using the network in a kind of receding horizon fashion. So we trained this the system, trained a neural network, or I guess more formally a distribution over neural networks to minimize the bound on expected cost that we get from PAC-based given a certain number of environments. And these are kind of what the environments look like. So they basically correspond to different instantiations of these cylindrical obstacles, also different positions, different orientations. And this is showing the performance of the learned controller on new environments that were not part of the training data set. And here are some numerical results. So the top row here is showing the number of environments that we use for training. So this is going from 1,000 to 4,000. And the bottom row here is showing the bound that we compute from PAC-based. So this is a bound on the success rate. So you can think of this as kind of 1 minus the cost, if you like. And success here just means avoiding the obstacles and getting to the other side of the track. So the bound that we're able to get here goes from around 75% to close to 80% for 4,000 training environments. And if we compare this with the true estimated success rate on new environments, you can estimate this just by kind of exhaustively sampling lots of new environments and seeing the success rate. This is around 82% or so. So yeah, we were pretty excited to see that some of this machinery from PAC-based is allowing us to get reasonably strong and also tight guarantees in the setting where we're trying to find a neural network policy and also where we have rich sensing modalities like RGBD. And I think traditionally making these kinds of generalization guarantees for neural networks in these contexts has been a challenging problem. We also implemented this on a hardware platform. So this is a Parrot swing drone. This is a kind of hybrid between a quadrotor and a fixed wing. And this the hardware system kind of mimics what you saw in simulation to some degree. We have these cylindrical objects set up in our lab space, for instance. And here we're giving the policy access to a depth image that sort of looks like this, or a depth map. In this case, the sensing is kind of simulated. So the payload that the robot has is pretty light, so not enough to put a real sense camera on, for instance. So we're using off-board sensing to simulate onboard depth sensing. But that's the only information that the policy has access to, just this, these depth images that are kind of from the perspective of the drone. And again, similar to the previous example, we're training a neural network-based policy or a distribution over neural network policies to optimize the back-based bound. And we train this purely in simulation. And then what you're going to see on the next slide are experiments on the actual hardware system. So for these kinds of environments, the guaranteed or success rate that we got from back-based is around 93%. And we tested the policies that we get on a number of different obstacle environments, so 30 different environments, and we found that the empirical success rate was 28 out of 30, so a little more than 93%. So the guarantees that we're getting from our theory kind of translate onto the real physical system. Here are some videos. So I'll keep the sound on because I think it's cool.
Ani, while we're watching, can I ask a question? What if this is really cool. What if I care about not just average costs in terms of safety?
Sorry, Sylvia, say that again. I think the audio was actually messing up what I could hear.
Sorry. I was just asking, what if I care not just about average costs on safety? If I care about kind of, you know, the worst case, keeping track of those.
Yeah, that's a good question. So actually, that was a failure case. In the video, yeah. So so currently, we're trying to make guarantees just on the expected cost. I think one potentially promising direction is to incorporate risk metrics, so things like CVAR, conditional value at risk. So I think that some of these frameworks could give you guarantees on risk as well, risk on new environments. I don't know if worst case necessarily is something we're going to be able to get, or if it's reasonable to ask for worst case guarantees, especially when you have like neural networks and perception kind of as part of your control loop. But yeah, I feel like CVAR or something like that might be the way to go.
Makes sense.
Good. Other questions? Okay. All right, so I guess one question I haven't really addressed yet is how do we specify the prior? So I mentioned that we have to have some prior distribution over hypotheses or policies in this case to kind of implement this back-based approach. And I feel like this is an important opportunity to embed some domain knowledge that we might have on our problem to improve the kind of guarantees that we can get from this framework. In the previous examples that I described, we chose relatively simple priors. So for the quad rotor example, we had a kind of simple base policy that just scores different motion primitives based on the depth. And we learned a kind of residual policy on top of that. And we just specified some Gaussian distributions on the weights of this neural network and chose a particular kind of standard deviation for those weights. Another approach that we've been thinking about a little bit more recently is can you learn the prior itself, maybe given some data, some prior data or some expert data, so via imitation learning. So we kind of implemented this approach on a grasping example. The setup here is we have our Franca Panda arm with a RGBD camera at the top. We collected a number of demonstrations from a human in a simulator using a 3D mouse. So these are demonstrations of grasping different mugs. And then we basically had another data set of mugs that we then used to find a policy, a posterior distribution or policies to optimize the back-based bound in simulation. And then we deployed this learned distribution over policies on the hardware platform with a number of different mugs that were different from what we saw during the training phase. And on this example, the guaranteed success rate that we get from back-based is around 93%. The prior, which is based purely on this imitation data, achieves only about an 83% success rate. But when you then find a posterior that optimizes the back-Bayes bound, we get around a 98% success rate in simulation, and kind of like a similar performance, similar success rate on the actual hardware platform. So you can see that these are the numbers on the table are basically 3 different random seeds. So we get 100%, 100%, and a 96% success rates on the hardware system. Okay, so I guess a couple of you mentioned this question of what happens if this assumption that we're making on the distribution of environments is violated. So what happens when the test environments that you deploy your system on, those environments are drawn from a different distribution than the training environments. And I think there are 2 kind of interesting questions here. So the first question is, can we even detect this? So can the robot detect basically that it's performing or is being deployed on environments that are out of distribution, so OOD detection. And this could potentially allow the robot to act more conservatively, for instance, on these new environments, or just cease its operations altogether and say, hey, I don't know what to do. I was trained on this set of environments, and now the environments that I'm encountering are coming from a different distribution, and maybe I should retrain. The other interesting question is, can we learn policies that are robust to distribution shifts, and can we make any kinds of guarantees in this setting? So let me talk about the first problem first. So how can we do out of distribution detection? So the kind of example that maybe is useful to have in mind is we train our drone to navigate through certain kinds of environments, maybe using the approach that I described. And then we deploy our drone on new environments, potentially with wind gusts that are changing the dynamics of the system, and potentially also on environments that are more cluttered than the environments that were used for training. And yeah, the goal here is just to detect, not necessarily to do anything with this information, but just to detect when the robot is operating in environments that are different from the distribution over training environments. And I think in this kind of problem, there are 2 criteria that we want any out of distribution detector to satisfy in these kinds of robotics contexts. The first is that we want some guaranteed confidence bounds. So in particular, we want some bounds on the false positive and false negative rates of our detector. So bounding, for instance, the probability that our detector says we're out of distribution when in fact we're within distribution, or vice versa. And the other kind of slightly more subtle, maybe criterion that we would like to satisfy is we would want our OOD detection scheme to be task relevant. So if you imagine, for instance, that your policy that you trained on the training distribution is not sensitive to colors of obstacles, but then in the test distribution, the colors of obstacles are different. This is not going to have any kind of adverse impact on the performance of your controller. And in this case, we actually don't want to say we're operating out of distribution, because this distribution shift is not one that's relevant to the task that the robot is performing. So we want to say we're out of distribution only when the performance of the robot is adversely impacted. So here's the overall approach that we've been pursuing. So the first stage will be identical to what I presented before. So we're going to train a policy in order to minimize a performance bound, so minimize a bound on the expected performance on the training distribution. We then deploy our policy on new environments. And basically, if we find that our performance bound is being violated on the new environments, then this gives us some confidence that we're operating out of distribution. And we can actually derive some kind of guaranteed confidence bounds depending on how much violation of the performance that you see at test time. So let me describe a little bit more carefully both of these 2 phases. So in the training phase, we're going to use the back-Bayes framework that I presented.
Sorry, Andy,
yes,
just to go back, there are 2 out of distribution faults. One is that the bound on failure is exceeded. The other one is that the bound on failure is you've got a distribution which is extraordinarily benign.
Yes, good, good.
Which is a different kind of failure.
Yes. Good, and so in this approach, we're going to care about the former. So we're going to be okay if we have a benign new distribution, because we're going to say everything is good. We don't need to kind of update our policy, and I'll show examples of that in a bit.
Yeah.
Good. Yeah. So on the training phase, we optimize a policy using this pack-based approach to minimize the expected cost on the training distribution. And in this case, it's actually more kind of beneficial to find not a distribution over policies, but a single policy that minimizes the expected cost. And there are pack-based bounds that allow you to do that, find a single policy instead of a distribution. And we're going to use a cost function here for this UAV example that corresponds to the minimum distance to the obstacles. And you can kind of estimate this based on a depth sensor, for instance. So the bound we will get is on the expected minimum distance to obstacles on new environments that are drawn from the training distribution. And again, we're going to use neural networks to parameterize our policies that map observations in the form of depth images to actions. So that's the training phase. In the testing phase, we're going to deploy this learned policy with the associated bound and the performance on a few, so maybe just a handful of test environments. So you can think of K as maybe being 5 or 10 or something like that. And the main kind of intuition is that we're going to look for violations of our performance bound on these test environments. So if we find that the average cost on the test environments is larger than the bound of the expected cost that we had on the training distribution, then this gives us confidence that we're operating out of distribution. And using some concentration inequalities, in this case, Hoeffding's inequality in particular, we can actually come up with a bound on the false positive rate of this detection scheme. So by false positive rate, I mean when the out of distribution detector says that we are out of distribution, when in fact the robot is operating within distribution.
So that's a calculation in the old probability distribution, not the new one, right?
Yes, correct. And there's a slightly different analysis technique, which also gives us a bound on the false negative rate. So this one is a little bit more subtle, but we can also bound the probability that we declare that we're within distribution when in fact we are out of distribution. So we can bound both of these kind of error rates, false positive and false negative. And the other kind of feature that I want to highlight here is that this detection scheme is task driven in the sense that I described a couple of slides ago. Since we're only looking at the impact on the cost, so the impact on the performance, if there are distribution shifts that are either benign, whether the cost doesn't go up, or maybe have no impact on the cost, then we're not going to detect these as being out of distribution, which I think is a desirable feature in these contexts. So we implemented this on the drone example, I guess, that I've been using to sketch out the approach. So we trained our policy using pack-based, and here we're increasing the wind, the amount of wind. There's a fan at the bottom left of the video. As you can see, as the kind of percentage of the wind increases, so the maximum 100% here corresponds to kind of 5 meters per second wind gusts. This has an impact on the cost. So you can see that the drone here gets closer and closer to the obstacles. So this plot here is showing basically our auto detection confidence as we increase the wind gust. The x-axis is the amount of wind. The y-axis you can think of as kind of like a confidence indicator that the robot is operating out of distribution. And here we have two slightly different statistical techniques that we're using. They end up performing kind of similarly. But the main takeaway here is as we increase the amount of wind, the confidence that the robot has that it's operating out of distribution keeps increasing. And then the example that I guess Bob mentioned with a benign distribution, we see that here. So we place the obstacles kind of far away from each other. And these are easier environments in a sense than the training distribution. And in this case, we don't detect these environments as being out of distribution because there's no adverse impact on the performance of the robot. Let me also show a manipulation example here. So we trained a neural network policy with an associated pack-based bound for grasping mugs. We then tested this policy out both on new mugs that were not part of the training data set, and also bowls, which are pretty different from the objects that were used for training. What you see on the x-axis here of this plot is the number of test objects. So the number of objects that the robot has to decide whether it's operating out of distribution or not. And the y-axis again is this indication, this confidence of being out of distribution. And the blue curves here are showing the confidence when you have mugs. So these are the same kind of distribution as the training objects. And the robot basically believes that it's operating within distribution as we would expect. For the red objects, the red curves, which are bowls, the robot pretty quickly realizes, so within just four or five trials, realizes that it's operating out of distribution and has a high confidence on that.
Quick question,
Okay,
Ani.
let me pause again, maybe
4 or 5 trials with the same bowl, or is these different, like 5?
Sorry, these are different bowls. So we give the robot access to like a handful of bowls, and based on the performance on these test environments, it has to decide whether these are out of distribution. That's a good question though, because I guess one of the things we've been thinking about is what happens if can you do this in an online fashion? So the way I described it, it's kind of like a batch approach. So you have some batch of test environments that you can run your policy on. But sometimes you want to do out of distribution detection just on a particular environment. And we're thinking about techniques for doing that as well. Right, let me see if there are other questions so far. Okay, so sorry, yes, go ahead.
So in this regard, your task relevancy comes from kind of the costs that you establish while operating, right?
Yes.
So is there any way to kind of detect this out of distribution stuff that you guys have looked at without actually failing online or without actually having some issues while operating?
Yeah, great question. So I guess the cost that we chose here is the distance to obstacles. So this is sort of like a continuous kind of indicator of success or failure. So we're not necessarily requiring that the robot will crash on new environments. But I think coming up with such a cost is an important kind of thing that we need to do as engineers for like a particular application domain. And I think it's more complicated in the case of manipulation. So in manipulation, I think what we've been thinking about is if you have tactile sensors, then maybe you can figure out how close to slipping your object is, and that could be turned into a kind of continuous like cost like indicator or performance indicator. Yeah, but it's definitely an important question. All right. So yeah, the second question that I mentioned kind of within this umbrella of what happens when your test environments are drawn from a different distribution is can we not just detect when we're operating out of distribution, but can we actually kind of proactively learn policies that will have some robustness to distribution shifts? So here's the setup. So again, just as before, we have some training distribution, which I'll refer to as D. We have some test distribution D prime. You have to make some assumptions about how the test distribution relates to the training distribution in order to say anything about the performance on your test distribution. So in this case, I'm going to make a simple assumption, which is that your test distribution, maybe we don't know exactly what it's going to be, but it's going to lie within a KL ball of your training distribution. The main technical idea then is to use what's known as the Domskar rather than change of measure formula which allows us to bound the expected cost on the test distribution d prime or some test distribution d prime as a combination of the KL divergence between test and training, which we're assuming is bounded, plus this term, which sort of looks like the entropic risk from robust control theory. And the kind of key point here is that this term depends only on the training distribution. So we can apply the techniques that I described before with Pac-Bayes and basically work with the exponentiated cost. So bound the expected exponentiated cost using Pac-Bayes theory. And this gives us a robust bound on the performance on the test distribution, assuming again that it's within this KL ball of the training distribution. So we implemented this on an example. This is an obstacle avoidance example with a Dubin's car type model with a range sensor, so a depth sensor. And in this case, training and test environments had a different distribution over the radii of obstacles in the environments. So I'm kind of plotting the probability density over radii of obstacles on the plot on the right. The training distribution assigns higher probability to lower radius obstacles and lower probability to higher radius obstacles. The test distribution is just a uniform distribution over the radii. So in a sense, the test distribution here is more difficult than the training distribution because we have a higher probability of seeing larger radii obstacles at test time. So these are the kinds of bounds we get if we combine Pac-Bayes with the approach that I sketched on the previous slide. The top row again is showing the number of environments we use for training. The bottom row is a robust bound of the success rate that we get, which ranges from about 72% for 500 training environments to about 82% for 10,000 environments. And this is assuming a particular kind of KL ball around the training distribution. So I think this is a reasonable approach, but there's a really important challenge here, which is that the scale divergence between test and training, this term could be extremely large. For example, if you have a test distribution over environments that differs purely in terms of colors, let's say of obstacles in the environment, and let's say your policy that you're training has kind of no sensitivity to colors. In this case, this is not a distribution shift that's going to have any impact on their performance. But if you think about, at least naively, the KL divergence between the distribution over test environments and the training distribution, then that KL divergence is going to be non-zero and potentially pretty large. And that might give you a vacuous or a kind of useless bound. So how can we address this challenge? And I'm just going to kind of quickly sketch something we've been thinking about recently. Which is to use, instead of the KL divergence, to use the Wasserstein metric. And the idea here is to basically learn a Wasserstein metric that captures purely task-relevant variations in the environment. So if you have two distributions that are different, maybe in terms of colors, which has no impact on your performance, the distance between these two distributions should be zero, ideally. And so we're basically, given some amount of data, we're learning a metric that encodes this property. And then given this metric, we're performing distributionally robust optimization with respect to the Wasserstein ball of a certain radius around the training distribution. And we can do this basically via adversarial generation of environments, so coming up with environments that adversarially mess up a policy that you have and doing this training in an iterative fashion. Yeah, I guess the main takeaway here is that we're kind of learning a metric, learning a Wasserstein metric, which assigns low distance to two distributions over environments that are kind of different in a non-task relevant manner. So we implemented this on a few different examples. This is showing a grasping example. And we compared this technique to other baselines, particularly based on domain randomization. And we found that this approach, based on distributionally robust optimization with the Wasserstein metric, performs better on this hardware example. Okay, good. So let me just end with some directions for current and future work that we're thinking about. So I think there's still a long way to go, particularly in terms of the strength of the guarantees that we're able to make with our frameworks. So the strongest guarantees that I presented in this talk were kind of at the 93–95% success rate, which I think is promising, given that we're making these guarantees on neural network policies and systems with rich sensory inputs. But of course, there's still a long way from the kinds of guarantees that we want to make for deploying these systems in real world environments. I think there are a few approaches for potentially coming up with stronger guarantees. The first one is just scale. So scaling up the size of our training data sets. And we've been working with some industry partners to scale up some of the theoretical approaches that I sketched today, particularly in the context of manipulation. Another kind of direction that I think is promising is to make guarantees that are more modular in nature. So in the work that I presented today, we're optimizing these fact-based bounds kind of in an end-to-end fashion. So we're finding policies that map directly from sensor inputs to actions in order to minimize or optimize the guarantees from fact-based. But I think one potentially interesting approach is to use generalization theory to make guarantees just on the perception part. So where you go from raw sensory inputs like images to some kind of state estimate, let's say, and then combining that with techniques from robust control to then have a guarantee on end-to-end performance. And I think this kind of approach potentially could give stronger guarantees than what I presented today. But I think finding exactly how to combine these two separate pieces is a challenging but exciting open problem. The other direction we've been thinking about is how do you specify priors, so embedding prior knowledge that we have as engineers to improve the strength of the guarantees that we can make. So I mentioned using imitation learning as a potential approach. Another approach might be to use meta-learning, so learning the prior given kind of experience from many different tasks. And another thing we've been looking at is using generative models. So if you have some distribution over environments, which maybe is not completely accurately representative of the true distribution over environments, but at least can give you some prior on the distribution of real world environments that your robot might encounter. I think another interesting theoretical question is, can we establish fundamental limits on generalization performance? So can we say for a given robotic task, if you have this bunch amount of data, then there's a fundamental limit on how well you can expect to generalize to new environments, no matter what learning algorithm you use, how big you make your neural network, and so on. And this seems like an interesting and relevant research question as well to think about. Okay, so just to conclude here, so I've presented some approaches based on fact-based theory for making generalization guarantees for systems with rich sensory inputs like vision or depth, hybrid or nonlinear dynamics, and importantly, neural network-based control policies. And I've also talked about some of our work on doing auto-distribution detection with guarantees on false positive and false negative rates, and also auto-distribution generalization. So hopefully I've convinced you that there's some exciting potential here to use some of these theoretical techniques to make guarantees on generalization and safety for learning-based control of robots. Here are some references if you're interested in exploring more. So some of the work on fact-based we presented at Coral last year and also at IGRR. And the work on auto-distribution detection we're presenting at the Conference on Robot Learning this coming November. And this work on distributionally robust policy learning with the Wasserstein metric is currently under review, but we have a preprint on archive. This is our research group at Princeton. So we have 7 PhD students, 1 postdoc. Postdoc Sushant has actually just accepted a position at NVIDIA as a senior research scientist. He's going to be working on the new autonomous vehicles team. So if you have students who are graduating soon, we're looking for postdocs, and feel free to send them my way. All right, so yeah, let me kind of end with this conclusion slide and take any further questions you might have. Thank you.
Yeah, I was looking at. Thanks. It's been an interesting seminar, and thinking about applications. The methods scare me. You need to have an appetite for failure. And so, looking at autonomous vehicles, it seems doubtful. It doesn't solve that problem. But I think about areas like telecommunications. Computer traffic control, to a lesser extent, even power systems. In communications, things fail all the time, and we recover and we're happy. So that might be an area to think about. Real world external environments where things change, but our appetite for failure is commensurate with the failure probabilities that you see. With the control problems, I can see how mostly what you've spoken about is state estimation or estimation and classification of the environment. It would be the control problems that there's an issue in system identification, which is, if you like, a much more formalized modeling exercise from data. And that is that the models that you fit in closed loop are different from those that you fit in open loop. Right. So in other words, you use closed loop data, you get a different answer than you would in closed loop. Closed loop data versus open loop data. And furthermore, the model that fits appropriately changes with the controller that you design. So it's a tough business. And you can really just creep around changing models, changing controllers. So there are some things which suggest caution in control.
Yeah, excellent points. I guess on the first one, appetite for failure, I think part of it potentially we could address via simulations. Like I guess autonomous car vehicles, vehicle companies often do quite a bit of the training in simulation environments, and maybe that could get us some way at least.
Yeah, I understand, but I think the problem is that you see, things which are out of distribution is the issue. I mean, it's the reasoning side of things that humans are good at. I'm just trying to identify systems like telecoms where failure is perfectly acceptable as long as it's not too frequent.
Yep. Yeah, that's fair. Yeah, and the system identification question is an interesting one. We haven't looked that much at that specific kind of sub-problem. We've been thinking about just kind of.
It's a hard one.
Yep. Yeah.
Now, I should say that Sylvia had to go to
office
hours. Yeah, so let me take over as the not as host. I don't need any power, but are there other questions?
We have one from Nikolai.
Yeah, maybe I can ask one more. So I've been thinking about this sampling of environments more, and I feel like if you want to consider robots operating in more and more general situations, you would need more and more samples. Yeah. The bound depends directly on N, and I imagine if you get more and more complicated scenarios, N will become astronomical. So I'm wondering, are there ways to think about decomposing the environments, or thinking again at some sensor level sampling instead of complete environments? Because if it's a really large environment, I can see like millions of variables.
Yeah, definitely. I think one approach that we've been thinking a little bit about is if you can basically make these kinds of guarantees on generalization for the perception system, and then take care of some of the variations in environments using these techniques, but then using techniques from robust control, for instance, for handling other kinds of variations in the environment. So I guess just as an example, if you have a drone that's doing obstacle avoidance, you could use some techniques from robust control for handling things like wind gusts. So you can say that if you have bounded wind gusts, then I can basically provide guarantees on how far away I'll get away from my kind of nominal trajectory that I'm trying to track. And so that way you don't have to kind of use pack-based or these techniques to handle that part. But then cases where you might benefit from learning, which I think have to do with the kind of geometry of the environment. It's hard to make robustness guarantees on that. That's potentially where like these kinds of techniques might be useful. So that's something we've been thinking about. But yeah, I'd be curious to hear your thoughts as well.
Yeah, thank you.
Other questions?
Yeah, I'm thinking about it still.
No more questions? We'll have to start offering a monetary prize for the students to ask questions. It used to be before we went to Zoom, we could just offer them pizzas and cookies. But no, as you can tell from the amount of back chat from the audience,
yeah.
It's been really an interesting and thought-provoking seminar, Arnie. I appreciate it. And yeah, I used to hang around with people like Peter Bartlett in the pack learning business. So I still don't quite understand how the Reverend Bays got into the picture, but thank you very much, and it's been great.
All right, thank you very much. Take care.